we're continuing with buffer. I mean, not buffers, but chapter 17 material. Actually, we'll do buffers, but not the buffer we looked at last time. What we want to do is we want to get a pH 7.00 buffer. And so we want a pH 7.00 buffer. And then, did I talk about optimum pH?
Yeah, optimum pH, optimum range.
Okay.
Desired pH, yeah.
All right, so this is what we want. And so what we have to do is we have to find an acid that has a pKa around 7. And so we'll need an acid with pKa around 7. It could be a little more, a little less, you know, depends. So let's take a look at some acids here that might work. So we're looking at the power of the Ka, and so here, that's 5. This one's may work. This is between 7 and 8, closer to 8 because it's 2.9 here. And so we could use hypochlorous acid and hypochlorite. That could work. What other options do we have? The other options would be, let's take a look at some of the polyprotics here. Well, either that or we can just look at the chart here. Let's look at the chart. This is close, 4.3 tungsten minus carbonic acid. Actually, this is old data. This is an old chart, 98. Let me pull up a more recent chart. Oh gosh. All right, well, I'll just look for the one in our book. I think this is table 16.5. Actually, they give us a pKa over here. So we're looking at the power. Like, for example, hydrosulfuric acid, if you look at that, that's perfect. Because the power is 7, coefficient is 1, so the pKa is going to be 7.00. This is perfect. And so this one would work very well. Except there's a problem. Even though this is perfect pKa value, the problem is H2S. H2S is toxic. Did I talk about this at all?
I think you briefly touched on it.
Okay, H2S is very toxic, and you don't have to wear the mask. I don't know either.
Yeah, it's
Yeah. And in fact, I don't know why they're still requiring everybody here to wear a mask. I think it's
I think it's just more political thing.
Yeah, I'd actually rather not wear mine either. Okay. Yeah, and so here, H2S, limited solubility, toxic, it's a gas, it's really hard to work with. And so even though this is perfect, this is not perfect. And so let's look at something else. Carbonic acid. The problem with carbonic acid is it's a gas. I mean, it decomposes into gas, CO2 and water, and it's not very soluble. And so this is very difficult to work with. And then we go down the list. This could be okay here. This would be monohydrogen citrate. And this is, yeah, between 6 and 7. So that could work. Here, this is 8. Dihydrogen phosphate, this could work too, because this is between 7 and 8. You know, closer to 7, because as we get closer to 10, 10 times 10 to the minus 8 is 1 times 10 to the minus 7. So closer to 7 than it is 8. And this is easy to work with. It's not terribly toxic, and so that would be good. Hydrogen sulfide. The problem with hydrogen sulfide, even though this is comparable, they're pretty comparable, hydrogen sulfide is a pretty good reducing agent, sulfide. And so this is probably the best phosphate. So we use that. And so hydrogen phosphate.
So, when we look at these, does the PK2 matter at all, or we're just looking solely at the PK1?
Solely, no, at any of them.
Okay.
Yeah. And so in this case, we're looking at the PKA2, 7.2. But it's tricky because we don't care about PKA1. The only reason is they want to keep them together, 1, 2, 3, because they're all related to phosphoric acid. But you can buy these. So for example, we can buy phosphoric acid pretty pure. We can buy sodium dihydrogen phosphate really pure too. We can buy sodium monohydrogen phosphate, and we can buy sodium phosphate. So we can buy each of these species individually and do what we want. And so you don't have to have 1 before 2. And so in fact, we'll just call it, rather than calling it PKA2, we can just call it the PKA of dihydrogen phosphate. And that would be the acid. It's an acid anion. And so if we take dihydrogen phosphate, then the PKA 7.20. It's a little bit high, but we can drop it down by adding a little more acid in the ratio. And that'll drop the pH down a little bit. And so what we have to do is we have to calculate the ratio that we need of base to acid. So the pH is equal to the pKa of the acid, dihydrogen phosphate, plus the log of the base to acid. And so what is the base here? So the conjugate base of dihydrogen phosphate.
That would be the HPO4 tonight.
Yeah, this would be the conjugate base. And so that would be the log HPO4 2 minus. Oops, did I record? Am I recording? Yeah. Over H2PO4 minus. But do you find that, like, this is regarding the homework, do you find the Zoom sessions, those helpful?
Yeah, they're extremely helpful.
Okay.
Especially because I know, for me personally, like, I take my time when I do the homework, so it takes me a lot longer. So when I do it, if I'm able to do them before I get on the Zoom session and see how you do them, I can find little shortcuts, so it helps me get through them quicker.
Okay. All right. So the desired pH is 7.00. The pKa is 7.20. And then we have the log of base to acid. These have to be conjugates. And so subtracting this from both sides, I get minus 0.20 is equal to the log of this. And that means the ratio of HPO4 2 minus to H2PO4 minus is equal to 10 to the minus 0.20. And so we can just plug that into the calculator. See what we get. 0.63096. What this is a ratio, so it's going to be 0.63096 to 1. So for every 1 part of acid, we need 0.63 parts of base. We can also flip this over. If we invert this ratio, what we get is 1.5849 over 1. Ivan, are you okay if I go no mask? I mean, if you're uncomfortable, I'll put it on the mask. It's just, it's tiring wearing a mask all day. So here we have 1 part, especially with the signs. 1 part of, actually, what did I do here?
So is that like saying, so if we flipped it, then that means that we just divided the acid by the base. So for every 1.5849.
I actually got it upside down, sorry.
Oh, okay.
What, this means for every 1 part of base, we need 1.5.
Right, yeah. So
Yeah, but I wrote it.
Oh, okay.
Sorry, I wrote it upside down. And so what it means is for every 1 part base, we need 1.5894, or anything that matches, etc. This ratio. And so we need a little bit more acid than base, and that's going to drop the pH down. Now, we're still in the optimum range, because the optimum range of this, this is the optimum pH. And then the optimum range, which is going to limit the ratio from getting too lopsided, it's going to keep it within a 10 to 1 or 1 to 10 ratio, is going to be between 6.20 to 8.20. And so this acid can make a buffer within this range without compromising one or the other too much. And so we're well within the range. And so this would be a 1 to 1.5 ratio. So what we'll do is we'll do a calculation here. Like we did for the acetic acid. So I'm going to make this buffer a little higher capacity. So this would be a little bit lower capacity because the concentrations are lower. We can make it a much lower capacity, like 0.063 to 0.01. Or we can make it higher, like 6.3 to 10. That would be very high. And the higher the capacity, the more resistant it is to change. And so I'm going to go with a 1 to 1.5 ratio base to acid. And so if we make this 1 molar base, which is HPO4 2 minus, and 1.5849 molar acid, H2PO4 minus, that should be okay. Now, I'm probably not going to make it this many digits, because measuring it out. Instead, what we'll probably do is we'll just say that this is going to be equal to about 1.58 molar. So if I made this buffer 1 molar and 1.58 molar, is it still pH 7? And so we can check that here. Is this still pH 7? And so the pH is equal to the pKa, actually, which is 7.20. Let's skip that step. Plus the log of base to acid. And so by making this only 1.58, will that work? And so let's take the log of 1 divided by 1.58 plus 7.2. Yeah, and I get the pH of 7.0013, so it's pretty close if I don't carry that many digits. All right, then what I'm going to do to this buffer is add 1 drop of 6 molar HCl. Let's see what happens. 0.05 milliliters. 6.0 molar HCl. And then what I'm going to do is I'm going to take 250 milliliters of the buffer solution. Of course, the more milliliters of buffer, the less. So there's 2 ways to increase the capacity of the buffer. One is to use higher concentrations here. We can increase the capacity. The other is just to use lots of buffers. So if instead of using 250 milliliters, I use the liter buffer, it's going to be expensive, but it have plenty of capacity just in terms of sheer volume. Okay, then in chapter 17, we always do step I. Sometimes it's not necessary, but most of the time it's necessary. Oh, actually, in this case, it's not necessary. Solution dilution. Solution dilution is not necessary because I already have a mixture of these, and these are the concentrations in that mixture. So normally to make this buffer, I have to mix these 2 together. And sometimes when you mix them together, you're mixing solutions. So we'll take one solution of one and another solution of the other. So the total volume changes. But in this case, this is not necessary. So not necessary. Oh, actually, this is necessary. Sorry. Why is this necessary?
Is that because we added the acid into the equation? So now
Right. On the one hand, you think, 1 drop to 250, is it going to make any difference? Not really. But 250 to 1 drop is going to make a huge difference. And so that's the main reason, but we have to do it. And so even though it might seem unnecessary for one, it's very necessary for the other. So we're going to have 250.05 milliliters here of total volume. And so the HCl, the solution dilution equation is the initial volume over the total new volume, 250.05. So we'll go from 0.05 to 250.05, the total volume. And the initial concentration is 6.0 molar. And so this is the same solution dilution we done earlier, I think. And so let's do that. 0.05 divided by 250.05 times 6. This gives me 1.1 molar. 1998 times 10 to the minus 3 molar. And so it's significantly diluted here. The others aren't going to be, so since we're doing solution dilution, we'll just do it for everything. And so this is not a very significant dilution. This fraction is called the dilution factor. And so when we compare the two, it's almost the same, 250 over 250.05. It's barely been diluted. And so the concentration should just be about the same. And so we'll do 1 molar this is HCl. We'll do 1 molar HPO4 2 minus next.
So 250 divided by 250.05. 0.9998.
So barely diluted. And then the other one is going to be a 250 to 250.05 dilution of 1.58 H2PO4 minus.
Times 1.58, 1.5797.
1.5797. So these are going to be our new concentrations before anything reacts. And so we'll have our HCl, HPO4, 2 minus, and H2PO4 minus. And then we have to figure out what's going to react. So that's step I. Then we go to step 1. Step 1 is we take the strongest acid and react it with the strongest base present. So the strongest acid present is going to be HCl. What's the strongest base present? Normally it's water, but in this case it's not. There's a stronger base than water.
I'm assuming it's going to be the HPO4.
Yeah. HPO4, 2 negative. And so the acid loses, so we'll form chloride, and the base gains, so we'll form H2PO4 minus. All right, so what we're going to do is we're going to carry all these over to the next step. So the HCl is going to go here. It's going to be 1.1998 times 10 to the minus 3. This is probably better written in decimal form. Then the HPO4 2 minus. I'm going to go here, 0.9998. The chloride is going to be 0 initially. And the H2PO4 minus is going to be 1.5797 more. All right, so the change, we have to look at what the K value for this is. So whenever we have a strong acid or a strong base, the K is large. And in this case, the K is going to be very, very large. Because when HCl reacts with water, we get a very large K value. But HPO4 2 minus is a much stronger base than water is, so it's going to be an even larger K value, which we'll call very, very large. It reacts to completion, but what reacts to completion? The limiting reagent reacts to completion. So what is the limiting reagent here in this particular reaction? It looks like the limiting reagent is going to be HCl. And so we're going to lose all of that, 0.00119988. And so we're going to be left with 0 molar. Okay. How much of the base reacted? Well, it's a 1-to-1 mole ratio, so it's going to be the same amount, 0.00119988. And so what's that going to leave us with here? 0.9998 minus 0.0011998. I get 0.9986. And then the chloride will end up with plus 0.0011998. And then the H2PO4 minus will have to add that. So it's going to be 1.5797 plus 0.0011998. So this gives us 1.5809. All right, then step 2 is to figure out what's left over. And so what is left over? Well, the strongest acid left over is H2PO4 minus. The strongest base left over is HPO4 2 minus. So if we took the strongest acid and reacted with the strongest base, you know what we're going to form? We're going to form, well, if we take dihydrogen phosphate plus monohydrogen phosphate, we're going to form this monohydrogen phosphate and dihydrogen phosphate. And so there's no change there. In fact, when we look at this here, do you recognize this? Solution. This is the acid and its conjugate base. So yeah, it's a buffer, and we call this an HH buffer, a Henderson-Hasselbalch buffer. Well, if it's an HH buffer, then what we can do is we can use the HH equation. And the pH is going to equal the pKa for the acid. The acid in this case is dihydrogen phosphate plus the log of the base. The base is monohydrogen phosphate, PO4 2 minus, and the acid is dihydrogen phosphate, so base to acid ratio. So we just plug in the numbers. The pKa is 7.20, and plus the log of the base, which is 0.9986, over the acid, 1.5809. The log of 0.9986 divided by 1.5809 plus 7.2. And so that gives us a pH of 7.00. Actually, no. I did it, sorry, I did it wrong.
Well, that's what I got. 7.0004871.
This one comes out negative.
Yeah.
And so then plus 7.2, right? So plus 7.2. Okay, that's right. 7.0005.
Yeah.
Know what you got?
Yeah. So it's a really small negative number, so it makes sense.
Okay. I guess it did down a little bit. Original pH was 7.0013. And we added a little bit of acid to it and went down to 7.0005. But it barely changed at this point. And so the pH is still pH 7.00. And so when we add 1 drop of HCl to 250 milliliters of unbuffered water, the pH changes by many orders of magnitude. But when we add 1 drop of HCl to this buffer has plenty of capacity to neutralize it. In fact, this minus here, minus x plus x here, maybe plus 0.998 plus. The bigger initial, the smaller the change is going to be. And so if we start off with even higher concentrations, then there's an even smaller change in the ratio, which results in an even smaller change in the pH. But this buffer has enough capacity to neutralize it. We could overwhelm it by adding too much. You know, if we add too much acid here, eventually we're going to hit the point where we're going to consume all of our base. And we'll have to see what's left over. What's going to happen is pH is going to change significantly. All right, so let's take a look at some other problems from chapter 17. The same thing happens with strong bases. If I had 1 drop of 6 molar sodium hydroxide, the H2PO4 minus would react with that and neutralize that alcohol with the pH change. Okay. Look at that sampling one more time. Okay, so number 1, for a solution that is 0.275 molar propionic acid or propanoic acid, the Ka 1.3 times 10 to the minus 5 and 0.0892 molar HI. Calculate the hydronium hydroxide propanoate. There should be a negative charge here. They're missing that. And iodide. And so this solution is a solution of a weak acid plus a strong acid. And so this is just a mixture of acids. So this is like a chapter 16 problem. If we have a mixture of acids and we're looking for all the hydronium ion producing steps, and we want to combine all the hydronium ion producing steps. And so which one is going to be the biggest contributor of hydronium? The strong acid, the weak acid, or water, Kw? Yeah, the strong acid is it. And so that's where we're going to start. We're going to start off with the biggest K, which would be the strongest acid. So this is going to be HI plus water. This is going to yield hydronium and iodide. K for this, well, this is Ka. Ka for strong acids is very, very large. And so it's going to be complete reaction here. So the initial 0.0892, 0 and 0. And so it's complete, so we're going to lose all of it to 0, and then we're going to gain 0.0892 more. All right, then we go on to the next step. The next step would be the next largest hydronium, which is either going to be the weak acid with K 10 to the minus 5 or water. But water is 10 to the minus 14. So for sure the propanoic acid is going to be much better. And so this will be the next step, step 2. Do the propanoic acid plus water. It's going to yield hydronium and propanoate. Propanoate is CH3, CH2COO minus. And Ka for this is 1.3 times 10 to the minus 5. If they're just asking for the hydronium, we don't want to do this stuff because the common ion effect. And so, how much? 0.275 molar. Well, one, we might do this step because we have a lot more weak acid than strong acid. The strong acid, we only have 0.0892. The weak acid, we have 0.275, so maybe it is significant. But then again, maybe it's not significant. It may not be significant because we're starting with common ion. And when we start with common ion, then there's going to be a Le Chatelier's style shift, but it's not really a shift because it's going to go right. It's just going to reduce how far right we go. Because we have to go right because the propanoate concentration is 0. And so this is called the common ion effect. Because of the common ion effect, we might not. On the other hand, because it's high concentration, we might. So let's go ahead and calculate it. So we have minus x plus x plus x. And so at equilibrium, we're going to have 0.275 minus x, 0.0892 plus x, and x. And so my Ka is going to be the hydronium, which is going to be 0.0892 plus x, times my propanoate, which is going to be x, divided by my propanoic acid, which is going to be 0.275 minus x. Okay, we're just going to go ahead and try a simplified assumption. We'll see if it works. So if we use a simplifying assumption, then this is going to simplify to 0.0892 times x over 0.275. And solve for x. It's going to be 1.3 times 10 to the minus 5. Times 0.275 divided by 0.0892. And x of 4.0078 times 10 to the minus 5. Which gives us a percent change equal to, which one's going to be the bigger percent change? X compared to 0.0892 or X compared to 0.275? Which one would yield the bigger percent change? Well, let's say if you had $275 and you lost a penny, versus if you had, let's say, if this were 275, this would be $89. And 89, well, a penny's not that big of a deal to either, but what would be a bigger percent change would be the 89. And so we'll do x over 0.0892. Because if this is not significant, then for sure this is not going to be significant. Times 100%. So let's calculate that. Divided by 0.0892 times 100. 4.4931 times 10 to the minus 2. 0.04. So this is 0.0449% change. And so the simplifying assumption worked quite well in this case. Let's take a look at what happens with the hydronium. So looking at the hydronium, we went 0.0892, and then in this step we're adding. We need 4 zeros, 1, 2, 3, 4, and then 4, 0, 0, 7, 8. And so we have 0.0892, 4, 0, 0, 7, 8. So we added a little bit. Was that significant? Well, let's see if it changed the pH much. And so let's calculate the pH.
So when we got our x, we got our percent change, and we used the concentration of the, we used the concentration of the hydronium. to find our percent change.
But yeah,
Okay.
But once we make the simplifying assumption, then we undo it, and we don't do the simplifying assumption here.
Right.
We actually do the calculation.
Right. And that gives us our
Yeah.
new concentration.
Right.
Okay, cool.
Well, let me, before I calculate the pH, let's just make sure this is correct. So we need to double check this. And so the concentration of propanoic acid is going to be 0.275 minus X. So 0.275 minus X, which is 4.0078 times 10 to the minus 5. Gives us 0.27496 molar. And then the propanoate concentrations is going to be this 4.0078 times 10 to the minus 5 molar. Okay, so let's double check to make sure. This is the proper K value. So 4.0078 times 10 to the minus 5 times 0.089240078 divided by 0.27496. So K comes out to 1.3008 times 10 to the minus 5. So it looks good. Now, should we go on to step 3?
Step 3 would be KW.
KW, right?
Yeah.
Actually, we have to go on to step 3 because
The hydro.
Yeah.
Not the
hydroxide, yeah. So we gotta go on to step 3. Now, if they didn't ask for the hydroxide, and let's say they only asked for the pH, what would the pH here have been? So let's figure out the pH. If I just stopped at step 1 and calculated my pH, I would have gotten a pH of 1.0496. 1.0496. By going on to step 2, I added a little bit of hydronium to that. So let's calculate the pH at the end of step 2, 0.0892. 40078. 1.0494. So pH is 1.0494, a tiny bit lower as we added a little bit more. But when we look at the sig figs, I'm only allowed 2 sig figs. And so this would have to be rounded to 1.05, and this one would have to be rounded to 1.05. And so if I were only interested in pH, it wouldn't have made a difference. The pH is dominated by the strong acid, unless this happens, unless the weak acid is highly concentrated relative to the strong acid. Like say the weak acid were, let's say, 3 molar, and the strong acid were nanomolar or micromolar, then the strong acid would be significant. Or 2, the Ka for the weak acid is not so weak. This is pretty weak, 10 to the minus 5. But we could have much stronger weak acids, like 10 to the minus 2, 10 to the minus 1. If the Ka for the weak acid were kind of big, like 10 to the minus 2 or 10 to the minus 1, maybe 10 to the minus 3, then we'd worry about it. Here, it's kind of small. All right, but anyway, we have to continue this because they're asking us for the inventory. So we're going to go on to the next step. So step 1, step 2, step 3. Step 3 is going to be the next hydronium ion contributor, which would be water. So this will just be H2O liquid plus H2O liquid. This is going to give us hydronium and hydroxide. We don't really expect much additional hydronium in this step, but we do expect some significant additional hydroxides, as we have none to begin with.
it's 0.089240078 and 0 molar. Change is going to be plus x, and so at equilibrium we're going to have 0.089240078 plus x. Kw is equal to 1.0 times 10 to the negative 14, which is going to be 0.089240078 plus x times x. Here we're going to use the SA, the simplifying assumption, so this is going to go to 0.089240078 times x.
So we'll take our Kw, this is 1 times 10 to the negative 14, divided by 0.08924. And that gives us an x of 1.1206 times 10 to the negative 13. All right, now the percent change is going to be x over the initial, which is 0.0892 times 100. It gives us 1.2557 times 10 to the minus 10%, which is insignificant. And so this works fine. It was a negligible change. So here we start off with 0.089240078. And then we're going to add, now we need 12 zeros, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then 811206. And this is going to give us 0.08924007800011206. So do you think that changes the pH at all? No. Did that change the hydronium much at all? No, it didn't change the hydronium much. Because if it did change the hydronium significantly, then step 3 perturbs step 1.
Right.
If step 3 perturbs step 1, then we have, step 3 perturbs step 2. If step 3 perturbs step 2, we have to solve this. Yeah. Also, step 2 didn't perturb step 1, but we don't care if step 1 cannot be perturbed. Strong species are unperturbed by the Chatelier's. And so, in other words, strong acids, strong bases go or react to completion. Case very large, so it's one-way reaction. And so here, yeah, this didn't perturb the previous steps, so we're okay. And then X is the hydroxide, so the hydroxide is going to be 1.1206 times 10 to the minus 13 molar. So let's make sure these numbers check out in our calculator. So I'll take the 1.1206 times 10 to the minus 13 times 0.08924007800011206. And that comes out right on. So our double check here, K is equal to 1. 0, 0, 0 times 10 to the negative 14. So that's it. So what we do is we find the species. So for example, HI, there's 0 molar left. H3O plus, we got to follow the chain here. And then we have this. This is our H3O plus concentration. We're only allowed 2 sig figs. And so we have around to 0.089 molar. The iodide concentration is here. Did they ask for iodide?
Yeah.
So iodide N is there at 0.0892. The propanoic acid concentration is here. Did they ask for that? They didn't ask for the propanoic, but this is what it would be. The propanoate concentration is here, and they did ask for that. So this would be propanoate. And then we have the hydronium, which ends here, and the hydroxide, which ends here. So we can plug those values to our answers. All right, so that's an inventory problem. Here. Okay. Let's take a look at the next problem here. The next problem is for a solution that is 0.164 molar in ammonia and 0.102 molar in ammonium chloride, calculate A, hydroxide, B, ammonium, C, chloride, D, hydronium. When you look at this, you see this is the base and it's conjugate acid. So this would be a Henderson-Hasselbalch buffer. So we could do a shortcut. If they're asking for the pH or the hydronium, we could figure that out quickly by using the Henderson-Hasselbalch. pH is equal to pKa of ammonium plus the log of the base, ammonium to acid ammonium ratio. We get the pH, and then from the pH we get the hydronium. From the hydronium we get the hydroxide, or from the pH we get the POH, and in turn get the hydroxide that way. But that doesn't give us the ammonium and the chloride. And so what we have to do is we have to do a full inventory. We can't take the shortcut Henderson-Hasselbalch equation for this. Now, when we have a mixture, we take the strongest acid, ammonium, react it with the strongest base, ammonia, but ammonium plus ammonia just yields ammonia and ammonium, so nothing changes. And so what that means is we have to do the Ka for ammonium and the Kb for ammonia. But I don't know if I talked about this before. And so let's take a look at doing the Ka for ammonium. It's ammonium chloride. Ammonium chloride is a soluble salt. Soluble salts are strong electrolytes. Strong electrolytes dissociate completely. You know, K is very large. For soluble salt, which are strong electrolytes. And then it's ammonium that does the Ka. So ammonium plus water yields ammonia plus hydronium, or hydronium plus ammonia. We also have ammonia, and so we have a Kb equation. Ammonia plus water yields ammonium plus hydroxide. And so do you see that these two are connected? In fact, these two describe the same equilibrium. These two describe the same equilibrium because they describe the equilibrium between ammonium and ammonia in terms of, in this case, pH. This also describes the equilibrium between ammonia and ammonium, but in this case, POH. And these two are tied together by pKw, which is 14.00. They have to add up to 14.00. And so, in other words, it describes the same equilibrium. Same equilibrium. And what that means is we could choose either. We could go with the Ka equation or the Kb, it doesn't matter. Because they're both the same. doesn't matter. But normally we like to pick the stronger species. So it turns out the KD for ammonia is 1.8 times 10 to the minus 5. So it's around 10 to the minus 5. Okay. If the KD for ammonia is 10 to the minus 5, what is the Ka for its conjugate acid? Well, it's got to be 10 to the minus 5. It's got to be 10 to the minus 9. Because 5 and 9 have to add up to 14. In other words, if the pKa actually and so what it works out to is this, ammonia is 1.8 times 10 to the minus 5, which makes ammonium about 5.6 times 10 to the minus 10. So that they add up to 14 or multiply out to 14. And so ammonia turns out to be stronger. So we probably should do this based on ammonia. Do you recognize this is the exact same position we were at when we derived the Henderson-Hasselbalch equation? When we had derived the Henderson-Hasselbalch equation, we had this exact system. Well, not exact, because we were using acetic acid and acetate, but it was the same type of deal. We could have used Ka for acetic acid or Kb for acetate, but not both. Because if you do both, then you're going in circles. I mean, you're just repeating yourself. You're doing the same thing. It's not necessary to do both, so choose one or the other. When we did the Henderson-Hasselbalch, we chose the Ka. Why? We chose the Ka because we want pH. Yeah. But we really should have chose the stronger K. And so we aren't going to do the Henderson-Hasselbalch for this one because they're asking for the inventory. So what we're going to do is we're just saying equilibrium. So we're going to choose the bigger K. So the Ka for this is 5.6 times 10 to the minus 10. The Kb for this is 1.8 times 10 to the minus 5. And so choose more dominant one. More dominant would be the larger K. Which would be the Kb. And so it would be that.
Times 10 to the negative 5?
Yeah.
Okay.
1.8 times 10 to the negative 5.
And since the KB is more dominant, then we're going
Yeah.
to start with that one.
Yeah, right. It's bigger, so. We'll start in the end. We only have to do one or the other, but not both. There's only one reason we do the more dominant one. The one reason we do the more dominant one is because this is going to produce more hydroxide than hydronium. This K is bigger than that K. When we finish that step, then we ask ourselves, will water contribute more? Will water be significant? Now, if this one's more dominant, we're going to produce a lot of hydroxide. Compared to this one, we'll produce minuscule amounts of hydronium. This is going to be more basic than it is acidic. So if we did Ka, the less dominant one, we're going to produce a tiny amount of hydronium.
which might fool us into thinking that KW is significant when KW is in reality not significant, because we should have been looking at, as a base solution, we should be looking at hydroxide producers. In a base solution, more basic solution, we don't look for the hydronium, we look for the hydroxide. And so these are my. So let's take a look.
Or could you say that if you started with Ka, would step 2 perturb step 1? Or would it not? That wouldn't be an adequate explanation.
What's your step 2? It would perturb it. If your step 2 is KW, if your step 2 is this one, but if your step 2 is KW, it would perturb it, but wrongly so. It perturb it because you're ignoring the hydroxide. It doesn't perturb the hydroxide at all. In fact, and so we should be looking at that. You know, if the acid were the dominant one and it did perturb, then we'd worry about that, and we'd have to do it simultaneously. We could go ahead and do this. You want to do this one with Ka?
No.
All right. We'll just do it with Kb. So NH3 plus H2O liquid. This is going to give us NH4 plus hydroxide. Okay, so in the initial, so in the problem, 0.102 for the ammonium and 0.164 for the ammonia. So this is going to be 0.164, 0.102, and 0. And so we can see we can take care of both in one equilibrium. We don't have to have two separate problems because both are present on this equilibrium. And so this is going to be minus x plus x plus x. And so that equilibrium is going to be 0.164 minus x, 0.102 plus x, and x more. And so this is Kb, which we decided to do 0.18 times 10 to the minus 5, which is going to equal 0.102 plus x times x over 0.164 minus x. We'll try the simplifying assumption because of the common effect here, 0.102 over 0.164 times x. I'm going to solve for x. It's 1.8 times 10 to the minus 5 times 0.164 divided by 0.102. And that gives us x value of 2.8941 times 10 to the negative 5. So which one would be a bigger percent change? X over 102 or x over 164?
102?
Yeah, so we need the bigger one. Bigger percent change, that is. Not the bigger initial. .0283%, so it's fine. There's no problem with this. So go ahead and calculate the concentrations here. So this is 0.164 minus our x value that we just calculated, 2.8941. So 0.164 minus 2.8941 times 10 to the minus 5. It gives me 0.16397. And we'll do 0.102 plus this. Let's do 0.102028941.
And then this will be 0.000028941. Okay. Let's double check the K value and make sure it's still, or make sure it does check out. Point 102028941 times point quadruple 28941 divided by 0.16397. And so that checks out. All right, in this solution, they're asking for the hydronium as well. And so we have to go on to the next step. Next step would be Ka. The next step is going to be Kw. I wouldn't expect it to contribute much hydroxide. This is 10 to the minus 5. Because of the common ion effect, we wouldn't expect much additional hydroxide. This K is so small, plus we have common ions we can. And so the initial will carry down from this step. Quadruple 28941. Hydronium 0. And so the change in the equilibrium. Change is going to be plus x. So equilibrium of x molar point quadruple 28941 plus 6. Kw is 1.0 times 10 to the negative 14, which is equal to x times quadruple 28941 plus x. We'll do the simplifying assumption here. SA is going to simplify to x times point quadruple 28941. Okay, let's go ahead and calculate x number here. So that's 1 times 10 to the negative 14 divided by point quadruple 28941. Which gives us the next value, 3.4553 times 10 to the minus 10. And so the percent change will just do order of magnitude. This is 10 to the minus 5 initial. So the change is 10.
I got 10 to the minus 12.
10 to the minus 12?
Yeah.
Okay, let me double check that.
Maybe I messed up something. That's 2.8. Oh, yeah, I messed up.
Okay.
Yeah, that's me.
Yeah. Okay. So the change is 10 to the minus 10. The initial is 10 to the minus 5, roughly, times 10 squared. So it's going to be about 10 to the minus 7%. 10 to the minus 7% is good. The hydronium did change significantly. There was no hydronium there to begin with. So we're going to end up with 3.4553 times 10 to the minus 10 more. But the hydroxide really didn't change significantly. This is going to be point quadruple 28941 plus our x, which is going to have 9 zeros, 1, 2, 3, 4, 5, 6, 7, 8, 9. So this barely changed. This is like 3 parts and 300,000. And so that's a very, very tiny change. Which is good because we don't want it to perturb the previous step. If this step perturbs the previous step, then it's going to be a problem. We can check if it perturbs it by just recalculating K with the needed hydroxide value. That's one way. Or we can just look to gauge the magnitude. Change. So let's double check our K value here. And it's pretty much right out there. All right, as far as the inventory goes, we can figure out the species here. So the ammonia is going to end here. The ammonium ends here. The hydroxide doesn't. The hydroxide carries down. The hydroxide is going to end here. And the hydronium ends here. So that's our inventory there. Okay, let's take a look at the next problem then. Chloride. Did I get the chloride? I didn't. I skipped that step. It's ammonium chloride. Ammonium chloride is soluble salt. Dissociates 100%. It's going to be 0.102 molar chloride. Calculate the change in pH that results from adding 0.100 molar sodium nitrite to 0.100 molar nitrous acid. This is going to form a Henderson-Hasselbalch buffer. And so originally we're going to have an acid, but we're adding its conjugate base, so the pH actually goes up a little bit when we do that. And so the answer is pH goes up. However, when we look at this is sodium nitrate to nitric acid. Now, this is a common ion problem. They're asking us to think in terms of common ion. So if I have nitrous acid and I add sodium nitrite to it, then we're going to get a Le Chatelier shift. And so initially I'm going to have 0.100 molar. Oh, we need to calculate. And so the easiest thing to do is just to reset it. So initially I could have nitrous acid, and this is going to be 0 and 0. And then I can calculate my equilibrium. And then for my equilibrium, what I can do is then I can add my sodium nitrite, and it's going to shift it to the left. When it shifts it to the left, it's going to decrease the hydronium, which increases the pH. But if they want us to calculate it, then this is the way to do it. I just
go ahead and calculate it here. I'd reset it and so that I have 0.100 molar nitrous acid and 0.100 molar nitrite. Okay, so I do the calculation in two ways. First calculation would be 0 and 0. This would give me the original pH. And then rather than trying to perturb the equilibrium conditions, I just reset the whole thing. And I'd reset it like this: HNO2 plus H2O liquid. This is going to give us H3O plus nitrate. And the way to reset it is assume that nothing's hydrolyzed. So this is going to be 0.100 molar. And this is going to be 0.100 molar. Okay. This is going to be 0. But when you look at this, this is an HH buffer. And we have equal amounts of base and acid, which means that the pH is just equal to pKa. pH is equal to the pKa of the acid. And so here we could take a shortcut since it's an HH buffer. We don't have to fill out the whole thing. And so we can see what the change in pH is from the original, which is with no common ion, and our new one, which is with common ion here. Now, for B here, it doesn't matter how much sodium nitrate we add. When we have a strong acid, it's one way. And so nitrate is not a good enough base to reverse it. Nitrite is, however. Nitrite will shift this equilibrium, but nitrate won't. And that's because K is very large. And so if we have nitric acid plus water, and we add some additional nitrate to this, will that help neutralize the acid? So if I add sodium nitrate, will that neutralize the acid? And the answer is no, because K is very large. K being very large is just a one-way reaction. And so we saw an example of something similar to this with HCl. Will chloride shift it back to the left? So if I dump in, let's say, sodium chloride, will chloride shift this back to the left? If it shifts it back to the left, that means we have decreasing hydronium. Decreasing hydronium means increasing pH, so we can help neutralize the acid. And so let's say you have too much hydronium, too much stomach acid. Could I consume sodium chloride to neutralize it as an antacid? No. In fact, there are two ways of thinking about it. One is strong acids are one way. Two is chloride is such a poor base we consider neutral, just like nitrate we consider neutral as well. Are we out of time? Okay. All right, so we'll just continue this next time. So exam on Thursday for chapter 16. Ivan, and just change it. Okay.